Okay. Yeah, I'll briefly introduce myself, and then I'll also briefly introduce the company that I work for called Recogni. I'll then talk about why we use Flyte, why we love using Flyte, and I'll highlight 3 key features that that we use very often, and to just make our lives a lot better. So I'm Fabio. I'm, as Samhita introduced me, senior software engineer at Recogni. I'm a member of the technical steering committee of Flyte. My background is in theoretical astrophysics, and before joining Recogni, I built up the MLOps team at a company called Aeronautics Momentum, where I also introduced Flyte. I'm based in Berlin, Germany. So Recogni. At Recogni, we develop neural network inference systems for the automotive driving industry or autonomous mobility applications. To the best of my knowledge, we have really unmatched performance amongst all of those automotive inference processing systems. For example, if I quote an MLPerf benchmark for single shot detection, like large object detection on 1200 times 2200 pixel inputs, we can run them on our systems at roughly 300 frames per second. And that at a very low power consumption of somewhere below 25 watts. So yeah, that is really it's really fast, really low energy, also very low latency. To make that happen, we have a patented processing system for neural networks that uses a logarithmic number system that allows us to greatly reduce the power consumption for the computations of neural networks. We are based in San Jose, in Silicon Valley, in California, and in Munich, in Germany. If you're interested about us, check out our website. I linked it here. I'll now talk a little bit about what our ML engineers do in their daily work. Also have a nice video here that shows it on the right. So we develop an in-house perception stack covering perception applications that are needed for autonomous mobility applications like classification, segmentation of driving scenes, 3D object detection, lane line detection in 3D, visual odometry, and others. And apart from developing this perception stack, our ML engineers also work on compressing and mathematically converting the models so that they can run on our hardware. And on the right here, you see 2 videos showing the same traffic scene. The top is a float neural network, and the bottom one is one that has been converted mathematically to run on our chip. I have another example here. The previous one was semantic segmentation. This one is 3D object detection. And on the right, you can see it in bird's eye view. Again, the top is a float model, regular float 32 model. The bottom one is one that has been compressed and converted for our chip. Probably it's very interrupted through the video because I guess when sharing the screen with Zoom, it's probably a bit interrupted. So to bring a float model onto our hardware, a few steps need to happen that we outlined here. So in the beginning, you have typically an O and an X graph of a float model and a calibration data set. And then we do post-training quantization with knowledge distillation using this on an X graph and this calibration data set, and out comes a model that has been converted mathematically converted for our hardware. And we have a compiler then that this converted model is the input for, and the compiler produces a so-called rex file, Recogni executable, and that one can then be uploaded to the hardware. So that's the process that our ML engineers typically do to bring float models to hardware. And that's also where Flyte helps us a lot for internal development. There are many steps here. Here it starts with the conversion of the float model, but even the float model needs to be produced in the first place, right? So we have workflows that automate everything from curating and pre-processing data sets, training float models, and then converting, compiling, and profiling them for our hardware. And since we're honing all aspects of that process, we need a platform for our ML engineers that allows them to self-serve their infrastructure, first of all, because we want to quickly try new approaches that might need very different infrastructure and hardware. And we want our ML engineers to do that in a self-serve manner. They might want to try a new architecture, need a different GPU type, different number of nodes. We want them to be able to do that on their own. And we want them to be able to automate everything so that our experiments are repeatable. We can change like small part and see what the outcome overall will be when the network runs on hardware. That's what we use Flyte for, basically automate everything. That's the motto. And that's why we love it. So I thought a bit about what I want to talk about, which features, and I will focus on three. The first one is distributed training and elastic training. The second one is pod templates, which in my opinion is one of the best features of the last half year probably. And then the last point that I'll highlight a bit is how we do continuous delivery for ML and how we use Flyte's cron schedule feature, which is a small feature, but I think it does great things for us. Okay. Talk a little bit about distributed training. So the data sets for autonomous driving applications are typically very large. And in order to speed up the training, we want to crunch through the data not on a single node or on a single GPU, but actually on a larger number. And Flyte integrates very nicely with Kubeflow's training operator, which provides custom resource definitions for Kubernetes for distributed training with the different deep learning frameworks. We use PyTorch, so we use Kubeflow's PyTorch job. And to our engineers, it looks like this here. So in the task decorator, they just say task config equals to PyTorch. They say how many workers they want, how many GPUs each worker needs to have, and that's basically it. The rest is handled by the platform that we provide. But to the engineers, it's all abstracted away, and they don't need to know the details of how the different workers are started, how they communicate with each other. That's really cool because it makes it very easy for ML engineers to use distributed training without having to deal with the details of the underlying ops tooling. One of the business requirements that we have is that we can also perform distributed, in quotation marks, training on when executing workflows locally on a single node, a workstation that you might have under your desk. And for that, we upstream the plugin to Flyte that uses TorchRun, which you can use locally to do distributed training in a local worker group, but you can also do it in a cluster, obviously. I captured a small video that shows what this does. So if you replace the task config PyTorch here that you have in your task decorator with the newer plugin called Elastic, we replaced PyTorch with Elastic here, and you provide the arguments that you would typically provide to TorchRun, then you can execute the workflow locally. That's something that you can't do with the PyTorch, with the existing PyTorch plugin. And then what happens is that something called Torch Distributed Elastic Launch, which is used to launch. Okay, I think I'll go a step back and explain what the cool thing is that's happening here. So when you use TorchRun or Elastic Training, you can have so-called local worker groups, which means that you run multiple processes on a single node, and then together with the worker groups on the other nodes, they form the entire world. That you can't do with the older version of Torch Distributed Training. So for example, let's say we want to train a model on 16 GPUs. You would, with vanilla Torch Distributed Training, start 16 containers. Each container gets one GPU, and then they communicate with each other. With TorchRun, you could say, for example, that you want to run only four nodes, 4 workers, but each worker gets 4 GPUs. And then within one node, one worker, or one pod in this case, we have 4 GPUs and run 4 sub-processes. So that the processes in that pod form a so-called local worker group. And the cool thing about that is that works also locally. So in the cluster, so in this scenario here, we want 4 workers and 4 processes per worker. So when you run that with Flyte in the cluster, you get 4 pods, and each pod runs 4 processes. So together it's 16. And when you replace the number of nodes with 1 here, then you can execute it locally. So nothing changes. You can, okay, now it's the wrong part of the video, but you can do Python workflow.py, and you get distributed training quotation marks locally. So you can use the same code, you just change 1 number, and you can go from running towards distributed training locally to running towards distributed in the cluster with more than 1 worker. So for us, that's really cool because it allows us to use the same workflow in a cluster where we have access to a large number of GPUs, but also on the workstation that we have under our desk where it's 2 or 4 maybe. And that flexibility is really cool. Yeah. Next topic. I'll talk about pod templates. So pod templates have been a feature in Flyte for a while. They were configured on the platform side. They could be configured on the entire platform level, on the project level, project and domain level, I think. I'm not sure if maybe even on the workflow level, but they were configured on the platform side. And since end of last year, beginning of this year, pod templates are exposed to the user as part of the task decorator, and that really gives a lot of power to users that I really like. And I'll show you 2 examples of what we do with that. So I think one concept that is very important in Flyte that I also really like is that it hides away the complexity of the underlying ops tooling from the users. And that's great because while Kubernetes is amazing, I don't think not everyone wants to use it, right? It's very verbose, and many ML engineers, they don't know how to work with it. And Flyte allows users to provision their infrastructure in a self-serve manner with Python. That makes it much easier to use. And here I have a task decorator where a user might want to request 1 GPU, and then Flyte turns this into a Kubernetes manifest for a pod. I need to move the videos, and it turns this description of a task here requesting 1 GPUs into a pod manifest, where in the resources section, 1 resource of type NVIDIA.com GPU is requested. And for us, that wasn't enough because our different perception applications are really optimized for different GPUs. And this didn't allow us to switch between, let's say, a T4 or a V100 or an A100 for different types of GPUs. So that was one of the key features that we needed while introducing Flyte at Recogni. And when pod templates got exposed to users by the task decorator, where we were able to do that. And I want to show you how here. So we wrote a small wrapper around Flyte's task called Recogni task, but it's really only a light wrapper. It provides an additional argument called GPU type. There's an enum that you can pass to it, different ones that are available in our cluster. And then in the Python code, but behind the scenes so that the user doesn't have to deal with it, we turn the GPU type, in this case, a V100, into a node selector that is understood by GKE, Google Kubernetes Engine. So the user says, hey, I want a GPU type V100, Python enum, and we, the platform engineers, then turn this into the pod template that has a node selector here. So with this feature, by exposing the pod templates to the users, we wrote a wrapper around Flyte's task that allows our users to switch between different GPU types, which was basically the only blocker why we couldn't roll it out to all teams at the same time, like when we first introduced it. We do 2 other things with Recogni task that I want to briefly talk about. We're just preventing that we run tasks on nodes that are more expensive than they would have to be. So what could happen, for example, is that somebody requests a node with 4 GPUs, the task finishes, task is still dangling, but then somebody else comes along and needs 1 GPU. Then the scheduler might say, hey, there's a 4 GPU node, perfect, let's just put the 1 GPU task on that one, preventing it from shutting down, and then we have 3 GPUs idling in the worst cases, nobody else needs GPUs. And to prevent that, we gave additional labels and taints to our node pools with the GPU type. Again, GKE doesn't do that by default. They only give a label. We also created a toleration for the type and the count. And then in the background, in this Recogni task here, we set the required node selectors and tolerations for these taints that we created. So in this case, that means that when somebody starts a node with 4 V100 GPUs, somebody that requests 2 can't use them, so we prevent that resources are dangling and not being used. One other thing that we do with pod templates that is really cool is that we control rather in detail how the different workers in elastic training are being scheduled. For example, so there are 2 things that I want to show you here. So when a user does recognize task config equals to elastic, so that's this PyTorch distributed training, we want 2 things to happen. The first thing we want to happen is that we want all the workers to start only if all workers can start. What do I mean by that? In these days of large language models and generative AI, GPUs in the cloud are a scarce resource, especially when you want to have the ones that have more memory, like A100s, for example. And let's imagine, for example, a scenario where 2 of our engineers, they start a distributed training with A100s, and they both need 20 of them. So that's a total of 40. And if we're unlucky, GKE doesn't give us these 20 because they themselves are out of A100 GPUs because people are training their large language models. So what could happen is that both start their training, both want 20 A100 GPUs, and worst case, both of them get 10. That means that neither of them can start, but both of them started partially, and then we get timeout errors and torch distributed. Nothing happens. We still paid for GPU hours. And yeah, that's not great, right? Like engineers are waiting, or they started in the evening and expect to have results the next morning, but then they didn't because both tasks didn't get enough resources, while one of them might have, right? The other one wouldn't have, but at least one of them could have maybe. So we wanted to solve this problem in a way that a distributed training task only starts when all the pods can start. And what we did is that we installed the so-called co-scheduling plugin, which comes from a Kubernetes special interest group, into the cluster, and we configured the Kubeflow training operator to use that scheduler. In the background, it creates a so-called pod group, which ensures that the pods only start when all of them basically get a node. And then in this Recogni task here, it sets the scheduler name to the scheduler plugin scheduler, making sure that for distributed training tasks, this alternative gang scheduler is being used. Another thing that we want to do when scheduling distributed training workers is making sure that they're placed physically close to each other on nodes. So latency is higher, and also you can pay for network egress when the workers of distributed training get scheduled in different zones, and we need regional clusters because of because it makes it more likely that we can get GPUs, right? Than in a single zone, but we don't want the workers of distributed training to end up in different zones. And for example, then what Recogni task does, it creates a label in scheduling group, and it just puts some random string there. We have to create this at registration time, unfortunately. It'd be nicer to do this at runtime. And then we also put an affinity into the pod template that says, hey, all pods that have that match the label selector scheduling group and this random ID, we want to be in the same zone, basically. It's very verbose here, but that's what it ultimately does. All the workers of that distributed training, they will end up in the same zone. And you can also configure things like compact placement, that even within the same zone, they're placed near to each other on server racks that are very close to each other, if you really want to get the last bit of performance out of it. And it's really nice that we can do this now at the task level, because before the pod template was exposed only on the project level. We could have created a different project for these things, right? But what happens then to a task that isn't distributed training that we need for saving a model? It wouldn't work if this thing then also has this pod affinity here, right? So yeah, basically the TLDR of this, I think it's great that Flyte hides away the complexity of Kubernetes because many people don't want to deal with it. But by exposing the pod template to the user, you give power users the ability to do what they want with raw manifests. And I think that gives us the best of both worlds. So that's really cool. Okay. The last topic or the last cool feature that I want to highlight is cron schedules. Might not sound like a big feature, but I think it's really cool what you can do with it. And our use case is that we want to detect regressions in ML performance very quickly. So we have, I didn't count, but quite a large number, but we have many ML engineers that work on a shared code base and develop their perception applications. And we want to prevent a scenario where one engineer makes a change and doesn't realize that it has some unwanted effect on somebody else's perception application. And then this gets discovered 3 months later. And then it's very hard to figure out which commit exactly introduced the regression, right? Because yeah, it will be very difficult to find that out then. So what we do is that, actually, I think I'll jump ahead to this slide here. So we register Flyte workflows in CI/CD. We do that anyways. Everything that is running on a feature or any workflow that is, let's say like this, any CI/CD pipeline running on a feature branch registers Flyte workflows in the Flyte development domain. Everything that runs on master builds, CI/CD builds, registers into the Flyte staging domain. And when we create GitHub releases, we register in the production domain. And I have this picture here from a really cool article from Google Cloud. Basically, the TLDR is it's great if you treat your ML workflows like something that you release. So have your workflow code, check it into a source code repository, and then in CI/CD register the pipeline and then run the pipeline. So don't do it don't treat it like a manually executed experiment that needs a human to be run. Treat it as something that's completely automated. You only do git commit, and then the rest is automated. That's the TLDR of this picture here. I think there's not enough time to go in more detail, but imagine it like this. Engineer checks in their workflow changes, make a PR, merge it, and then on the master build, we register this in the Flyte staging domain with the cron schedule, and then this gets executed on the schedule. So might look like this in Python code. The engineer would define their workflow here at the top, add workflow, and overwrote workflow name here, maybe not a good idea, and define some cron schedule, which is either for us it's a weekly or a nightly if there's a lot of development on that application. And that means that every night or every week we run the latest version of we train the latest version of a certain perception application. We log metrics and losses and statistics into 1DB, and then we also compare to the last run and to the best run, and then automatically alert on Slack if there's a regression. And that allows us to detect rather quickly when we introduce a change that either leads to a 5% F1 score drop, for example, or leads to memory consumption doubling or training time to triple or whatever. We'll notice these things right away. And then it's typically not a large number of commits that we need to check to find out which one it was. And by registering workflows in CI/CD and then having these cron schedules that we run regularly, I think it helps us a lot to improve certain metrics that we're interested in over time and not risk regressions there. And with these launch plans here, with the cron schedule, I think it's pretty easy to do that, which is very nice. Maybe one last word about this. What I'd like is that automatically always the last version gets run, so you don't need to worry about deactivating previous ones. You just register with PyFlyte register Python module that creates these lines of code here, and then the last version on master is the one that we execute. It's pretty convenient. Okay, yeah, I talked a bit about a company that I work for called Recogni. We develop crazy fast inference processing systems for autonomous mobility applications. and we developed perception tooling and conversion compilation tooling to bring networks onto our hardware. I talked a bit why we use Flyte for that, and then I highlighted three key features that we like a lot, which are distributed training and elastic training, pod templates, which really allow power users to do whatever they want with the Kubernetes pods, and lastly, cron schedules that allow us to detect regressions pretty early. And yeah, I want to thank you for listening to what we do. And if you have any questions, I'm happy to answer them.